Hello guys, welcome to my YouTube channel and I hope that you will be really very fine this day. Today I'm gonna make you learn how to implement the De Morgan law or prove the De Morgan statement in quartus 15. In my previous video I've showed you how to implement or prove the De Morgan law in Proteus. So today we are using the quartus 15 software. So let's open it. Here it is opened. So now the first thing you have to do is to just click on the file and then project wizard, click next. Here you should name your project without using any space. So I'm renaming this file according to my name. You can name it anyway. So it is saying that my file is already existing, so I'm going to delete the file and continue using the new project. So here then next, and then again click next. So next. So one change you have to do here is click on the verilog HDL and then click next and then finish. So quartus is opening the project, so it will take a little bit time. So now it's open, so you have to click just new and then click the verilog HDL file and then click OK. So here you can see that the screen white screen is appearing here, and now you have to just I've already made the code, so I'm just going to copy and paste the code. So here is the De Morgan statement that states that the product of two input logic states, and by taking its complement, will be equal to the addition of the complemented values. So the second equation states that if the two products are coming, and by taking its complement will be equal to the product of the x complement and y complement. So this is the module statement that is necessary to be written in the front of the code. It is just like the functions that mostly the C++ language demands. So the module name should be given as you have given the name to your file that to your project. So this name should be same, otherwise there will be an error in your code. So there will be the total number of variables that you are using in your code. So I'm just using the four variables. The input variables are x and y, and the output variables are w and z. So w and z will be used to denote the right hand side and the left hand side of the first equation. First I'm going to just implement this equation, and then I will implement this equation and then let you know how does this work. So first equation, by using this first equation, I'm using here the x dot y. So generally the dot operation is done by the AND gate. So the AND symbol is generally the AND shortcut symbol that you use in the simple language. So this is the AND, x and y, and the complement denotes the negation. So the negation is the sign here. You have to just click shift, and then there will be the button that is on the right side of the one number key. You can use this sign from there. So this is the left hand side, and the right hand side is this. Generally the plus operation or the addition operation is done by the OR gate. So the OR gate symbol is this, and the complemented values are these and these. So x complement and y complement. So here I've just pasted the AND module. It is used to you can say and the program. When we not use it, it will compile the empty lines, so it will be difficult for you to just compile the code. So I'm just going to run this starting the compilation. So let's see what's happened. Click yes, and then save it this file to the location where you want. I'm just opening it and then saving it. Yes. So it has started compiling. It will take 1 minute or 1 minute and a half, so be patient. So it is showing us compile, design and analysis synthesis error, the semicolon sign here. So let's compile it again. So the code is now successfully compiled. Let's see its output. So the code has now successfully compiled. So you will, after that, if you want to see the output in the binary form, you have to click the university program VWF and then click OK. So after that, click on the edit file and then insert node, then node finder, then click the list. So the list here is appear, then you have to transfer it on the graph. So click here and then click OK and then click OK. So here the sequence wise alphabetic order is appeared, but you should notice that W is the output and Z is the output, but the both inputs are X and Y. So if we want to adjust its time, so here you should click the 25 or whatever, 100. Let's suppose 100 I'm putting here, and then we have to just put here 50. So here you can see that when we are dealing with the binary forms, generally the 2 raised to power n terms are involved. So in binary there are 2 inputs, then 2 raised to power 4 terms will be involved in binary form. Let's suppose here is a 1 and here is a 0 and here is a 0 and here is 1 and is 1 1 and 0 0. So the 4 logic states are accomplishing the needs for that. So after that you have to just compile it here, just click on the run timing simulation and then click yes, save the waveform. So the output waveform will be automatically appeared. The waveform will be appeared here successfully after the compilation. So here you can see that the Z and the W are showing the same types of the logic states. Here you can see that it is the W and it is Z. So the De Morgan law is proved. You can see that W is at 1 logic state, and here is also the 1 logic state wave is appearing, and then it goes to the 0 and then goes to 0. So here is 1. So these waves are similar, so you can say that the De Morgan law is proved. So next move on to the circuit. If we want to make the circuit, then there is the file name that you have already made, then click on the locate node and then click on the locate in RTL viewer. So the circuit that is made from the code will be automatically appeared here. So here you can see that these are the 2 inputs and the outputs here. These circles are shown by the NOT gate, and then the OR gate is attached, and then the AND gate, the NOT gate is attached to the output of the AND gate. So this is the whole equation for the De Morgan law. Hence the first equation of De Morgan law is proved. Now move on the second equation for the De Morgan's law. The only change that we have to make is first I am going to close all the windows that I've previously opened. Now I'm going to implement this equation. It is defining that the plus of x and y and the taking its complement will be equal to the product of x complement and y complement. So here you can see that a little bit change that we have to make is plus. The plus operation is generally performed by the OR gate, so we have to just put the OR gate symbol like this, and the multiplication operation is performed by the AND gate, so we have to put here the AND symbol. So here is the only change, and this is the change for the second equation, so I am writing it here. Here is the second equation. So I'm just going to compile it in the same way as the previous ones. So it will take a little bit time to be compiled. So now it is successfully compiled. So go on to the verilog university program VWF and then click OK. So then click edit again, do the same process, then node finder, then list, and then give it list this, and then click OK and then OK. So alphabetical arrangement like the previous one is appearing here. So you have to just click the timer and then set the frequency like this, 100 period, and then it is the half of the above. It should be the half of the above, and then you can see here, oh sorry, there is a big mistake. It should be 50 in order to complete the requirements for the logic states. So Here you can see that the waves are appearing. So now let's start its simulation and then save the waveform pattern. After successful compilation, you will see that the waveform output will be appeared, so it will take a bit time. So here is the output that are at the topmost and the bottommost. So you can see that the outputs waveform are similar in pattern, where there is 1 and there is 1, where there is 0 and there is 0, and there is 1, there is 1, and there is 0, 0. So the similar pattern is observed. So you can see that, you can say that this De Morgan law is proved. So move on to the circuit. I will let you know and click in the RTL viewer. So here the circuit will be formed which you have coded. So here are the input terminals, which for the both equations, it means that x into y complement, and it is stating that x plus y whole complement. So this is the circuit for this. So let's implement the different functions on this. That are 4 in logic state. There are 4 different inputs. These are the 2 different inputs. So I will go to this, and then I'm just removing this. So now I move on to the 4 inputs for x, y. Sorry, I will rename it as A, B, C, D, and the output will be denoted by, let's suppose, f. This is the function for that. The output will be denoted by f. So I have to just write this component, these integer values, or whatever you can say, the variables in this form, in this function that's predefined: a, b, c, and d, and f. So output is f. So I will assign the f the value of the function that I am using here. The function, for the sake of simplicity, I am just going to change this code a little bit. So here let's suppose we are going to implement this function. It's a complement into b plus c complement into d. So let's make it a simple one. So the complement sign is showing that a, it's smaller a, and the multiplication sign is done by the AND operation. So AND b, and then we will use this OR function, that is generally the plus function, and then again minus c and d. So this is the function that I have coded here. So let's compile it and see what's happened. So now it has successfully compiled. Now move on to the graph of this function. Just click on the university program VWF, and then we will see that inserting the node here, and then node finder, and then list. I'm just doing it again and again in order to make you learn how to use this with full. So here I've used. So after the successful compilation for this function, now move on to so then after clicking on the OK, the A terminal, B terminal, C terminal in the alphabetical order will be appeared here. So let's set its time. For example, I'm setting its time to, let's suppose, 25, and then setting its time to the double of the previous value is 50. Again, the double of the previous value is 50 into 2. Okay, and then the double of the 100 is 200. So here the logic states will be like this, because you see that when you are making the truth table for the 4 logic states, so 2 raised to power 4 and the 16 possible combinations will be appear. So as same as when you see that this type of combinations, when you study the full wave like this is completing the full wave from here to here, then in this area you will see the 16 possible combinations of these 4 waves. So after that, compile it, output like this will be appeared here. uh, well while going to the circuit, again repeat the same process. Click on RTL viewer and you will see that the circuit here that we have implemented on equations will be appeared here. This is the F that is producing in the result of the combination of these two AND gates and one OR gate with each other. There is the A0 and B0 and then D and C. So I hope that you will really enjoy this video, and don't forget to like, share and subscribe my channel as well. Stay tuned for the more updates.